Hello everybody, and today we are going to be talking about how to approach 2D kinematics questions by going through a series of examples, as well as the thought process that you should have going into each unique physics question, depending on what it's asking and the context of the question. So let's go ahead and get started as to how you should start approaching these questions before we dive into solving a few for examples. So let's go ahead and get started. So the first thing that you want to do when you are approaching these 2D kinematics physics questions is you have to recognize that there is both the x and the y direction. And in both of those directions, there are 5 key variables that will help to keep track of other variables as we solve for the unknowns using the kinematic equations from one-dimension kinematics. So for each x and y, there's going to be unique values of displacement, or delta x or delta y, unique values of the initial and the final velocity, as well as an acceleration and a time variable. Now the time variable is the only thing that applies to both the x and y, but in the y direction there's going to be unique values of displacement, the initial velocity, the final velocity, and acceleration. An important note about acceleration is that in the y direction it's usually gravity, which is negative 9.8 meters per second. So the acceleration in the y direction is usually 9.8 meters per second squared. And that is an important thing to know, as a lot of these questions imply that you have that knowledge in mind. So let's go ahead and write down our 3 kinematic equations. Sometimes these are going to be on your answer sheet or your cheat sheet that a teacher gives you during an exam. However, if you do not have this, or if it's a AP test, you are going to have to memorize these equations. So the first one that we have here is the velocity final is equal to the velocity initial plus the acceleration times time. The second one we have is the displacement in whatever direction you're dealing with is equal to the initial velocity times time plus 1/2 a times t squared. In that case, you have to be careful that there is not an initial position. If there is an initial position, make sure you add it to that right side. And finally, we have our timeless equation, which is the velocity final squared is equal to the velocity initial squared plus 2 times the acceleration times the displacement in whatever direction you're dealing with. So oftentimes you will see me represent some of these variables with an additional subscript designating the direction that the velocity final is. Instead of just saying VF, I might write something like VFX, which shows that it's the velocity final in the x direction, or the acceleration in the y direction like I wrote over here. So that is just to help organize your variables. And again, another important thing to know going forward as we go ahead and take a look at a couple examples here is that if you have 3 of any of these variables, you are going to be able to solve for the other 2 in that direction. So if you are able to find time, let's say in the x direction, you could use that and use it in the y variables to help solve for any unknown variables in the y direction. So understanding that and being able to work backwards to get the solution that you want is an important concept that you have to know going forward. So let's go ahead and take a look at a couple of examples now. A ball is launched off a cliff at an angle of 45 degrees above the horizontal. The cliff is 10 meters high and the ball has an initial velocity of 30 meters per second. A wall that extends into the sky is placed 25 meters from the base of the cliff. How high up the wall does the ball hit? So let's go ahead and draw a picture together that will help visualize what this question looks like and sort of what we are solving for. And then you can go ahead and try to solve this on your own and then compare your answer later in the video. So let's go ahead and write out a little diagram here. So we have a cliff with a ball being launched off. So we can draw a little ramp there, and it is being launched upwards at 30 meters per second. And this angle here is 45 degrees. This distance that the cliff is above the ground is 10 meters. And we know that it travels in the horizontal 25 meters because there is a wall that is extending into the sky that is going to intercept the ball. So what we want to find in this question is the delta y in this case, once the ball has reached the 25 meter displacement in the x direction. So go ahead and think about what kinematic equations you're going to use here, what the steps are going to be to solve this, and if you don't know, just keep watching this tutorial and hopefully it'll help clarify some things. Alright, so the first step we want to do is draw out that little T diagram that we had before, where we have the x and the y direction, right? So we have the x and the y direction, and we are going to write down our variables. So we have delta x, we have velocity initial in the x direction, velocity final, acceleration, and time. Same thing for the y direction. We're going to write out our variables. We have velocity initial, velocity final, acceleration, and time. So in the x direction, we know that our displacement is going to be 25 meters. In the velocity initial, we are going to derive that here. So let's go ahead and do that real quick. I'll write out a bigger diagram here, which will help visualize what the velocities look like. So we have 45 degrees here, and 30 meters per second is our launch velocity. So now we have to break this down into the x and y components, because 30 meters per second at an angle does not tell us anything about the x and y velocity. So we're going to use trig in order to get those velocities. So using SOHCAHTOA rules, if you don't know those rules, you can look up a video on our channel that'll help better explain that. But here I'm just going to write out what these velocities are. So we have 30 cosine 45 degrees in the x direction, and then we have 30 sine 45 degrees in the y direction. So if both of those numbers are positive, it's going to the right, so it's treating as the positive x direction, and it's going up 30 times sine 45. And if you don't know the unit circle, 45 degrees is the same in both the x and y. It is root 2 over 2 for both the x and the y. So we are going to use that numeric expression to break down the velocities. And let's go ahead and figure out what that is going to be. So it looks like that is going to be 21.2 meters per second for both the x and the y direction. So let's go ahead and write that out. And again, this question is asking how high up the wall does the ball hit? So we are trying to find our delta y. So I'll write a question mark there to help remind us. In the x direction, our velocity final we know is going to be some number. We don't know what it's going to be. And in the y direction, we also don't know. We can't assume that it's 0 because we look at the moment of impact. So the ball is traveling at some speed at the moment of impact. But in the x direction, we actually are able to understand what that velocity is going to be, because in physics kinematics, we assume that there is no air resistance in these types of problems, because that would add a unnecessary layer that would add complexity to the question. So the velocity final in the x direction is still 21.2, which means the acceleration is 0, and time is going to be a variable that we're going to solve for. So in the x direction, let's go ahead and use an equation that has time. So let's go ahead and use delta x is equal to velocity initial in the x direction times time plus 1/2 times the acceleration in the x direction times time squared. Okay, so now we are able to solve for time based on what we know here. So in the x direction, we know it's going to travel 25 meters, and the initial velocity is 21.2 meters per second, and then we have time. And notice that the acceleration is 0 in the x direction, and it's also going to be 0 here, so this whole term goes to 0. So now we have 25 is equal to 21.2 times t, and it looks like t is going to be just over 1 second. Let's go ahead and get an exact numeric answer here, and this is going to help solve for delta y in the end. So this is sort of that backtracking I was talking about that's going to help solve for delta y in the end. So we get the time is 1.179 seconds. And let's go ahead and clear some space up here. Okay, so now we know time is 1.179 seconds. We can go ahead and write that on the y side here. So we have 1.179 seconds. And the acceleration in the y direction, this is under the acceleration of gravity, which is negative 9.8 meters per second squared. Notice how we have 3 out of the 5 components necessary to solve for the other 2. So now we can actually get delta y. We're going to use the exact same equation that we used before for solving for time for delta x, but now we're going to solve for delta y. You're going to see how this works because all of the components that we need are already there, and we're just going to plug and chug. So let's go ahead and take a look at what this answer is going to be. How high up the wall does the ball hit? So we have delta y is equal to the initial velocity times time. We know both of those, plus 1/2 times the acceleration times time squared. We know all of those components, and if we want to add those little subscripts of y into all of those components that could change between x and y, we can, just to remind ourselves that we are working in the vertical direction here. So we have delta y is equal to the initial velocity of y, which is 21.2, times time, which is 1.179, plus 1/2 times the acceleration of gravity, negative 9.8, times time squared, which is 1.179 squared. Now let's go ahead and punch that in our calculator. 21.2 times 1.179 gives us about 25, and negative 9.8 times 1/2 is about negative 5, times 1.179 squared. That gives us about negative 7. But we cannot forget the initial condition here. We have to remember that the cliff is 10 meters high, so we are adding an additional 10 meters, which is that x naught, right? So, or in this case, it'd be the y naught. So that is that 10 meters of additional heights that we are adding on top of the origin. So our answer would normally be 18, but in this case, this is one of those trick questions that the physics departments at your school or university like to throw at you. They like to include these little things just so you get your answer wrong at the very end when you see your answer in the multiple choice box. So make sure that you add your 10 meters to your final answer so you get a delta y is equal to 28 meters. And that is your final answer. Let's go ahead and take a look at one more example. A box that is being dropped from a 100-meter tall building and is thrown downwards at a speed of 40 meters per second. Halfway down the building, the box hits an opening window, launching it horizontally at 2 meters per second, but it is still falling downwards at the same speed that it was falling before. Now the question is asking how far from the base of the building does that box land? So let's go ahead and draw out a little picture here where we have a building with a box that is falling at an initial speed of 40 meters per second. We're going to go ahead and make that negative and treat down as the negative direction. Then at the halfway point, or at 50 meters, it hits an open window, and then it is given a horizontal component of 2 meters per second. And now it is asking how far from the base of the building does the box land. So we have to figure out how long it takes for this box to fall first. So we have to get time first, and then we are going to determine what that displacement in the x direction is going to be, because we know the velocity in the x direction does not change. So velocity x initial is going to equal velocity x final. So both of those conditions are going to prove true for this question, as well as many others you're going to see. So first, this can actually be treated as a one-dimensional kinematics question if we are just looking at the vertical direction. So we know delta y is equal to 100 meters, which is the height of the building. We know acceleration is equal to negative 9.8 meters per second squared. And we also know that the velocity initial in the y direction is equal to negative 40 meters per second. The velocity final in the y direction we do not know, and time we do not know. But if you look, we have 3 of those components, so we are able to solve for the other 2. Let's go ahead and use the same equation that we've been using, where we get delta y is equal to the velocity initial times time, plus 1/2 times the acceleration times time squared. Delta y is 100, the initial velocity is negative 40 times time, and we have 1/2 times the acceleration. We can just simplify that down to negative 10 in terms of simplification. It's minus 5t squared. Now this looks like a simple quadratic, so we can go ahead and rearrange this function to get 0 is equal to 5t squared plus 40t plus 100. So we have to be careful here, as I accidentally made this y direction positive, but remember we are treating down as the negative direction. So the displacement in the y direction is actually negative 100. So we have negative 100 is the delta y. Let's go ahead and rearrange that equation. So now we get 0 is equal to 5t squared plus 40t minus 100. And now let's go ahead and factor that. You can factor it in any way that you want. You can divide it by 5. I am going to use a program here which will allow me to get the answer a little bit quicker. So we should get a positive value for our time, and we are left with two answers. We either have t is 2 or t is negative 10. So we can immediately exclude negative 10 because we know that's not right. So we have t is equal to 2 seconds. So now this is a pretty simple equation. Now we are just going to understand that it's going to take 2 seconds to fall. So if in the horizontal direction the box is traveling at 2 meters per second, and we know this statement up here is true, we can just write delta x is equal to velocity times time. So delta x is equal to 2 meters per second times 2 seconds. Delta x is equal to 4 meters. So that just goes back to using our prior knowledge, understanding that the displacement is equal to the velocity times time. And this is a prime example of a question that goes back to the one-dimensional kinematics phase. So dipping into that knowledge of how to get time in a one-dimension setting and then applying it to another dimension. So that's sort of the essence of 2D kinematics, is preparing you for these types of questions where you don't know exactly what's going to happen, but drawing a picture and understanding what equations you can use, understanding that you can know 3 out of the 5 components to solve for the other 2 in any direction are key critical components to solving these questions correctly and efficiently. Thank you for checking out this video. If you are looking for any other useful physics videos, go ahead and check out our channel. Make sure you leave a like and subscribe to receive future updates for any new videos that we release. Thank you.